covered in the meantime. And so here is what's going to happen in the next couple of weeks, modulo Thanksgiving, when we're all going to be relaxing, I hope. We're going to be covering 3 completely brand new lectures, and we're going to try to guide you really on what's happening in knowledge graphs and machine learning in the last year or so. So we thought, this is not going to be part of the exam, clearly. It's not going to be covered by any homework, so I really want to give you an idea of what's the bleeding edge in research in the field right now, okay? So today we're going to be talking about reasoning over the knowledge graphs. I covered this topic very briefly during the first month when we talked about node embeddings, and we just talked about how to embed entities and relations in a knowledge graph. Today we're going to go much more in depth, and we're going to be talking how you answer queries on a knowledge graph, okay? So let me give you a rough outline of the lecture today. Hopefully we're going to be able to go through all this material. I'm going to give once again a brief intro about knowledge graphs. Then we're going to be talking about the problem of why it's important to complete them. Then we go through a couple of classes of very important queries, path queries and conjunctive queries. And then we end with a brand new paper coming from our group called Query to Box, which will allow us to reason over the knowledge graph through box embeddings, okay? So this is our rough outline. Now, once again, what is a knowledge graph? We saw it a month ago, so it's clearly represented in a graph form. It helps us to capture entities, types, relationship, and in our case, the nodes are the entities in our graph, and usually our nodes are labeled with types. This could be gender of a person or anything else, and then the edges between our nodes capture certain relationship between these entities, okay? So like this could be a family relationship or daughter, son, and so forth, okay? Now, what are some examples of knowledge graphs that we already seen in one shape or another? You might even be using them in your projects. Very famous one is bibliographic networks, network of citations among papers. In this case, the node types are paper, titles, author, conferences, and so forth. And then the relation types will be this paper has been published in this venue, or this paper has been written by a specific set of authors, and so forth, okay? So one type of, let's call them specialized knowledge graph, okay? This covers a very specific topic. Another one, slightly broader, is a social network graph, which can be seen once again as a knowledge graph. In this case, our node types are going to be, people, what they like on Facebook, songs, food, and so forth. And the relation types clearly can be the friendship edges. They could be that they like a certain page on Facebook, that they're watching a certain movie, and so forth, okay? So once again, a social network in some sense can be seen as a slightly broader knowledge graph compared to what we saw in the last slide. And then what Google did a few years ago, and I think they were one of the first to brand this kind of common concept, the fact that you can model knowledge to a graph. They called it knowledge graph, and they said, you know what, we're going to be using it in our search system, because at the end of the day, it's extremely useful that you're able to connect such entities together with labeled relations that tell you why are these two entities actually related to each other, okay? So basically, Google started to use this kind of data structure as part of the features that make a difference when it comes to return very good web results. So Google, let's say, was the predecessor, but then clearly all the big companies tagged along. So, Amazon had their own product graph. Facebook is exposing a public API called the Facebook Graph API, and so forth. Basically, any major company you will visit, and if you care about talking of these topics, they will have their own instance of a knowledge graph, okay? Now, why are they important? Why do even companies care so much about them? So, first of all, they are very useful to serve information, okay? So this is the example that I was making about Google before. So here we have, for instance, we have our query, latest films by the director of Titanic, and then, in this way, basically, the search engine, rather than, having to dig through Wikipedia pages and try to understand what the query is about, will just walk through the knowledge graph, find out that it's James Cameron, if I recall correctly, I hope I'm not wrong, and then find all the other movies that this guy has directed. And very similar scenarios, can be found in other queries. So that's one of the main reasons why a lot of companies are working very hard on this problem. Another thing that you might be familiar with, that you have seen in chatbots, this happens very often also with mobile apps. So there are these new conversation agents that where you can ask specific questions that you care about, and they will try to give you back an answer which is pretty much in a natural language shape. But what's happening in the back end in reality is that they extract the key entities out of your questions, and then they map them to the knowledge graph, and they use that graph to answer your query. So let's go through this example. You're asking, I want to travel to New York in 2 days before Thanksgiving, staying for a week. And then, you will have this process in the back end that allows you to say, okay, Thanksgiving is a date, New York is a city, week is a time span, and so forth. And then you map this entity in your knowledge graph, and it will allow you to, for instance, say, okay, Thanksgiving in reality is this specific date, or New York means he or she wants to fly from the JFK airport, and so forth, okay? So another very cool application of why knowledge graphs are so useful. All right, so I convinced you why we care about this topic and why we're going to go through all of this today. So before venturing ourselves into how do we answer queries on the knowledge graph, let's talk about the completion problem and why it is so important. So if you go and download some of the publicly available knowledge graphs, for instance, there is Freebase that Google contributed for a lot of years, and now it has been discontinued a while ago. There is Wikidata, which is the current effort from the Wikimedia Foundation, so all the people who are behind Wikipedia. And if you've ever been on Wikipedia, you saw that there is this right box on pretty much each article that contains structured information. So what they're doing, they decided, instead of having humans actually editing all these info boxes in different languages, let's have one repository with all the information, okay? So they built a knowledge graph which they call Wikidata. That's a very cool resource available online, and so forth. And all these other examples are pretty much all based on Wikipedia. Now, what are the common characteristics of these data sets that you can download by yourself? They're all massive, okay? We're talking about millions of nodes and edges, tens of thousands of relation types, and so forth, okay? So incredibly interesting data to analyze. Now, as always, there is a downside. They're incomplete, okay? So many of the true edges are missing in this data set. And the reason why is very intuitive. Like, whenever you have a massive knowledge graph, it's very expensive to enumerate all the possible facts, okay? And the reason is, most of these facts are coming from humans who are writing them down, okay? So they're saying like, Barack Obama's wife is person X and Y, and born in this place, this date, and so forth. This takes a lot of effort. So you can expect that people, or in general entities that are very common, will have a good coverage of all their properties, but then the long tail will be severely under-described. So what we want to do is start from this data, which is incomplete but still very interesting, and move to a model that will allow us to predict plausible but missing links. Now, the key fact here is that we want them to be plausible, okay? Because in reality, we could take all the entities in this knowledge graph, connect them together, by assigning probabilities to each node, and then we will get an incredibly dense graph, so pretty much a click, and then we will decide, okay, we only traverse those edges that have high probability, okay? But this will become a graph that is immediately intractable as soon as it grows to a few tens of thousands of nodes, okay? So that's why we want to be in this situation where we predict only the plausible ones. How do we do this, and why is it so important? So let's go through one of the examples that was mentioned before, okay? So let's take Freebase, which I told you stopped being developed a while ago, but it already grew back then to this amazing size, so 50 million entities, almost 40,000 relation types, and 3 billion facts or triples, so 3 billion edges in our graph. Now, if you go and analyze, for instance, all the persons, so all the person entities in this graph from Freebase, you will find out that 93% of them have no place of birth, and 78% have no nationality. And for a graph that is complete, you would expect this not to happen, right? Like each single person will have a birthplace, will have a date of birth, and nationality, and so forth, okay? So, and this problem happens already with people. Imagine with other entities that have many more possible properties. So for this reason, something that we're going to be using a couple of times today is this Freebase 15K dataset, which is basically something that researchers built over time. They try to find a almost complete subset of Freebase, which they use in their papers to train their models, okay? So whenever I refer to FB15K or FB15K 237, which means only using 237 relation types. That's what I mean, okay? So, and the reason why we do it is we cannot really train on something as incomplete as this data set, okay? We need a good starting point. But this problem stands, so that's why we care about doing completion, okay? Because all these important facts are missing in the data. Now let's go back to one of the examples that I showed you a month ago. So we had this, very small subgraph coming from like let's say an authorship graph where we have authors, books, the genre that they write about, and so forth. And we said, okay, Stephen King is writing about science fiction, but we will also expect J.K. Rowling to have an edge connecting to science fiction, okay? And this link was missing. Now, why is this problem even more complicated than standard link prediction? We're not only predicting that there is a link between these two entities, but we also have to predict the relation type, okay? So that's why the space of the complexity grows much more, because it's not only about all the possible links that you have on the graph, but it's also about all the possible relation types that you can predict, okay? So that's why it's a cool and difficult problem. How did we work out this solution a while ago? So we said, okay, we have our knowledge graph. We represent each edge as a triple. So our HRT, H is the head, R is the relation, T is our tail. And then the key idea is we said we model each entity and relation as a vector in our embedding space, okay? So we decide the dimensionality of our embedding space, and then we map each single element of our triple to this embedding space. And our goal ultimately is the fact that whenever we embed H plus R, you remember this translation intuition coming from Transy, this embedding should be close to the embedding of our tail entity, okay? So what we learned back then is how do we embed HR, and how do we define the closeness between these two vectors. So for those of you who forgot a bit about Transy, I'm going to give a super quick refresher in a while, okay? Now, another important thing is not only the fact that we want to find out how to model, how to embed this relation, but another aspect that we didn't have time to cover the last time is that this relation can have different properties, okay? So we see very often in knowledge graphs certain common patterns among these relations. So one of them that you can think about immediately is the fact that certain relations are going to be symmetric. Okay? So if you have a property that tells you the two of us are family, then of course also the symmetric of that relation is valid. Similar thing about roommates and so forth. Okay? So certain relations belong to that class. Then we also care about the composition relation. Okay? Some of these properties, for instance, you can think that the mother's husband is my father. Okay? So you can walk through these two relations in a row, or you can just say that our R3 is this person is my father, okay? So this is how you compose two relations into one. And then also, last but not the least, some relations are n-ary, okay? So we could have a one-to-many, a many-to-one. So for example, you could say that R is students of a certain institution. So you will have Stanford, students of, and then n nodes representing all the Stanford students, okay? So this is not going to be a one-to-one, but it's going to be a one-to-many relation. So can we find a model that not only allow us to work with a simple one-to-one, non-symmetric, non-compositional properties, but also supports all of these? And we're going to see that it's feasible, but it will take us a bit of time, okay, to support all of them. So let's go back to Transy, okay, which we have seen a while ago. You have done homework, so I'm sure you still remember. So we can go very fast through that. Just one catch, throughout the whole lecture, we're going to be using this notation. Basically, whenever we're working with an embedding vector, okay, it's going to be in boldface, okay? So when it's just italic, it means that we're talking about the actual entity. And when it's bold, we're talking about the vector that we embedded in our embedding space. So now let's go back to Transy. We were leveraging this translation intuition, right? We said we have our head entity, and then we apply the relation, and this should bring us in the embedding space to our tail entity, okay? So this is the translation process in Transy. And our score function was basically just the distance between where the relation brings us from the head, minus the actual vector of the tail entity, okay? So if the L2 distance between them is low, then we know that our embedding is working correctly, okay? So here we have the example. Our head entity is Obama, then we apply the relation, nationality, and this will bring us to American, okay? So that's the gist of the idea of how TransZ was working. And we said, how do we train it? We had this very simple loss function where what we do is we have both valid triples and corrupted triples. We are taking the distance between them, and basically what we want is that the distance between the corrupted triples is very high, and the distance of the valid triples is very low, okay? And if you recall, we also had this term gamma at the beginning, which we call margin, and you can think of gamma basically as the smallest distance tolerated by the model between a valid triple and a corrupted one, okay? So in some sense, it's kind of a regularization factor. We will know that once the distance between the valid and the corrupted ones is within that gamma, then our training will stop, okay? Otherwise, it can go on until basically everything collapses to 0. And for more details, go back to lecture 7, as I was mentioning before, and you will have also the pseudocode for TransZ and so forth. But let's keep in mind basically how this loss function looks like, okay? Because we're going to be reusing it until the end of the lecture. So I've been talking about graph completion, so knowledge graph completion, or in general the fact that we should predict links in this graph. Now, how do we actually do it? You know, so we talk about that's how you use TransZ to embed your entities and your relations. Now, once we train it, how do we actually use these embeddings to predict plausible facts in our knowledge graph? So it's extremely simple. So let's go through a couple of examples. For instance, you know, we have this query which is who has won the Turing Award, okay? So what we do here is our head entity is Turing Award, then we have the win relationship, and this will bring us in a certain area of our embedding space. And what we find here, we're going to find that the neighbors of the Q vector are Pearl, Hinton, Banjo, you know, a lot of other people that have won the Turing Award in the last decades, okay? And basically what happens is we find the entities that are in the neighborhood, so they are close enough to our query, and we just connect them, okay? So in the resulting knowledge graph, what we're going to do is if there was no Turing Award win Banjo triple in the initial knowledge graph, we're going to be adding the triple, okay? So as simple as that. Same you can think of here. So we're going to go through this example multiple times. Canadian citizen projects here. You find multiple people, both Turing Award winners, some funny outliers, and all of them will be added to the knowledge graph in case they were not existing. All clear up to now? Any questions? Perfect. OK, let's move forward. Now, let's talk about the properties that are actually possible that we can model with TransZ, and the property types that instead we cannot model with TransZ. Question?
In the previous slide, how do you decide the radius of the circle?
Great question. So how do we decide the radius of this circle? This is one of the hyperparameters of your model that you, in general, you will decide yourself. There are some other techniques that we are not going to have time to see where also this parameter is learned. But you know, in general, you can derive this radius by common sense. Okay, so if basically you see how many neighbors it returns, that certain radius size, and you see if it's a meaningful result or not. But I agree with you that there is no, you know, recipe on how to choose it perfectly, and that's the reason why if we have a lot of added triples to our knowledge graph, it can become dense very quickly. Okay, so if this radius is big, then each query will return like hundreds of thousands of candidates, and all of a sudden we will have too many edges in our knowledge graph. Okay, great. All right, so as we were saying, let's see the different relation types that we can support with TransZ. So composition relations, are they supported? The answer is yes. So very easy to visualize why. X is our head entity. We do the first translation by applying R1, we go to Y. Second relation, R2, we go to Z. And we basically say, OK, R3 is nothing but the sum of R1 plus R2. OK, so R1 plus R2 should give us the same result of applying R3 directly. So TransZ can naturally model composition relations. And that's as far as the good story goes, because everything else now is going to be not supported by TransZ. So unfortunately, the symmetric relations are not supported. And why is that the case? So let's think about that example on top. Okay, so symmetric means that if we have this relation that goes from the head to the tail, we want exactly the same result from a relation that goes from the tail to the head, right? And to make this happen, we have to make r equal to 0, okay? And once we do that, we are basically squashing together h and t, okay? So we're saying to TransZ that h and t should be exactly the same entity, okay? So we lose basically the ability to model different entities when there is a symmetric relation between them, okay? So this is the first problem in terms of what kind of relation types we can model. The second one is we also have problem with n-array relations. So let's go through this example. Let's think about this as, again, like the Stanford students. So H is Stanford, R is student of, T1 is one of the students, same thing, HR, T2, T2 is another student. Both of these relations exist in the knowledge graph. The problem is that with TransZ, T1 and T2 will map to the same vector, okay? Because the starting point is the same, the head is the same, the relation is the same, so we will have only a single translation, and all these nodes will all be mapped together, okay? So basically, when we apply our translation, this is going to be contradictory, because we don't want T1 to be equal to T2, okay? So if you take something like FreeBase, and there are certain nodes like male, and then there is a gender relation, and all these edges point to all the male people in the knowledge base, optimizing for that loss function in TransZ will squash all the people together in the same node. Okay, so that's why TransZ is not powerful enough to work with something like a very diverse graph like FreeBase. All okay until now? Okay, then let's jump to TransR. So I'm going to show you a slightly more advanced model. There is actually a class of techniques called TransX. Okay, so you will find a lot of them, H, R, and so forth. So each one of them proposes a slightly variation of the TransZ model, which was the very first one. So for this lecture, we selected TransR because it's very nicely complementary to TransZ. So it's able to model the other two type of relations that we couldn't cover before. I'm not going to go into detail. I put the paper down here in case you're interested. The key idea is instead of having both the nodes, so the entities and the relation mapped to the same embedding space, we're going to have different embedding spaces, okay? So there will be the standard embedding space for our entities, so it's d-dimensional, and then we will model each relation as a vector R in a relation space, okay? So each relation will have its own embedding space. As you can imagine, this leads to many more parameters, so clearly this is a more powerful model, it's a more expressive model. And this will allow us now not to have anymore some of the issues that we discussed before, okay? So basically, every time, instead of having a translation, we are multiplying by a matrix, which is our matrix representing a certain relation, and then this brings us to a different embedding space, okay? So this is the equivalent of TransZ, but applied with TransR. Now we see that in this case, we can model symmetric relations because every time we go with a different property, we're going to have a different embedding space for that property. We can also work correctly with n-array relations, but unfortunately, it's not going to support compositionality. And the reason is quite intuitive here. The fact is, for instance, the mother relation is in a certain embedding space, and then the husband relation is going to be in a separate embedding space. We're not going to be able to just sum together these two relations and concatenate them, okay? So basically, there is no natural compositionality for multiple relations in TransR. But what is the good news, okay? That if you recall what we've seen, basically, TransZ was supporting compositionality, TransR supports symmetry and one-to-many. So combined together, they allow us to model all these three different key properties. Now, one cool thing, if you want to complete a knowledge graph in a in a better way compared to just using TransZ, what you could do is you embed only normal properties that don't match any of the normal relations that don't match any of these properties, plus the compositional ones with trans Z, and then you leave out the properties that are symmetric and one or n-ary, and you map them, you model them with trans R, and then you complete them with the trans R embeddings. Okay, so this is one way in which you can solve the problem. By the end of today, I'm going to show you a model that supports all the three of them. Okay, so that ideally you can do a graph completion through that model that supports all of them. Okay, so this is for the completion, and then we can move next. Question? 2 slides. Yeah.
Oh, sorry, one more slide. So does that imply that there's no longer restriction in transport that embeddings are of norm 1, like in trans Z?
So you said, does this imply that the embeddings are of norm 1?
There's no longer a constraint that the embeddings are...
There is no longer a constraint, yes, correct.
R can be 0.
Here R can be 0, yes.
Yeah. And there's so different relations can have different dimensions.
Of course, yeah, they go in a completely different embedding space, each relation. So if you wanted, you could even have a different number of dimensions per relation.
R and MR here.
Correct. Yeah, I don't recall people trying to have different number of dimensions per relation. It will just make your model even harder to train, but ideally I don't see any reason why you couldn't do that.
Oh, so wait, is MR the same for all different types of relations?
No, M is a matrix per relation type. Okay, yeah, so that's why I said ideally if you wanted you could have even different dimensions, but I don't see any reason why that would help. Okay. Okay. Question?
Do you learn it in the same way as trans Z? Just to enforce
Oh yes, yes. Everything that we're gonna be seeing today has a very similarly shaped loss function where we take valid triples and corrupted ones, and then we make sure that the loss on the valid is very low and the loss on the corrupted ones is very high, and that we make sure that we learn our embeddings in the right way.
If you have enough training samples, could you learn the composition relationship?
If you have enough learning examples, do you learn the composition relationship? What do you mean by that?
Because you said the trans R is not good at composition relationships.
Oh, so not good means the following. It's just that if you leave in the data set some of these properties, some of these relations that have the compositional property, they will not be learned in the correct way. Okay? So, and this goes to the extent that, as we mentioned before, for instance, if you have these n-ary relationships and you learn them in trans Z, then it will squash all the students together. Okay, so basically you want to leave out certain relations because after the training they will have embeddings that are useless for certain entities. Okay. Question.
Another question was trans R, in that it's incapable of doing the composition logic. I think the reason why is that because they're having a rotation matrix, and if you add 2 rotation matrix, it does not make sense.
Of course, yeah.
If you change the operator with just like combine the 2 rotation matrix to just rotate the sum of the angles, would that make sense in this case?
Perfect. Yeah. So basically, you're asking, can we use rotate, which you have seen either in the exam or in the homework, if I recall correctly? In the exam, right? Okay. Yeah. So the idea that you have in mind is exactly rotate, where the mapping is not going to be done anymore into different embedding spaces. You will work in complex space, and the operation there will be an actual rotation. Yeah. So that's the additional idea. The reason why we wanted to cover rotated, but this lecture is very long. Rotated actually supports composition, but still does bad on the other 2. So I just wanted to get the minimal possible subset that will cover the 3 different property types we care about. Okay? Yeah, great question.
On these examples, we are actually training on the complete graph and then predicting on the incomplete.
Yes, so these examples are trained on the complete, and usually we do the inference step still on the same graph with certain edges removed. I'm gonna guide you through an experiment at the end of this lecture so you see how it actually works. But in reality, yes, you can train this model, for instance, on Facebook on Freebase Complete, and then you try to apply to the large one with mixed results. Like it's not still powerful enough to do well on the full Freebase graph. Okay, great question. Okay, let's move forward. So let's talk about pet queries now. Okay, so this is kind of query. First of all, I'm going to give you a taxonomy of all the different query types we're going to be seeing today. So in general, we want to be able to do multi-hop reasoning on a knowledge graph, okay? Which is a let's say a very how to say a very daunting task in some sense, because the one-hop queries are relatively easy. So we want to ask, where did Hinton graduate? But then it can start to be something as, where did Canadians with Turing Award graduate? Where did Canadians with Turing Award and Nobel Prize graduate, and so forth. This list could go forward, like you can keep on expressing queries that are much harder, that don't all use first-order logic, but for today we're going to be barely able to cover these ones, and they're already extremely hard when you're working on a large graph, okay? So first example, we're going to be talking about one-hop queries. And what we want is not only the fact that we can answer them efficiently, so we don't want something that takes minutes to run on a large knowledge graph, because as we said before, search engines are using this, so we have to answer in a matter of milliseconds. But we also want to make sure that they work on incomplete massive knowledge graphs, okay? That's why we care about the completion task before. Question?
Are we talking about also the difficulty of translating like natural language into understanding which nodes you're talking about? So like, for example, where did Hinton graduate could be rephrased as like, where did Hinton get his degree, for example?
Great question. The answer is, unfortunately, no. That's called query grounding. Yeah. I don't know which course covers this at Stanford. Maybe 224N, some of the techniques you can learn from there. In general, the easy way in which you can think about it, you do entity extraction from your questions, okay? So you're gonna find that Hinton is a person, and you will try to have a list of possible relations such as graduate. It's much harder than that, because if you go through Freebase, for example, some of the property names are not very well chosen, let's put it in a polite way, okay? And also between different knowledge graphs, there is no easy mapping between relation types. So it makes your life much harder. But the whole area is called query grounding. There's a lot of work going on there. Yeah, great question, thanks. Okay, so let's go from with the one-hop queries. So one-hop queries, again, the easiest possible query that we can try to answer, and we can formulate them as a link prediction problem, okay? So what we were talking about before when we said, is this HRT link true, okay? Is the same as saying, is T a good answer for the query HR, okay? Because we go from this head entity, apply the relation, and then we find, is T a right answer or not? And that's the same as saying, is that edge present in the knowledge graph or not, okay? So that's the one-hop query. Now, we used a one-hop query to generalize for our pet queries, okay? And what we do is we just add more relations on the pet, okay? So basically, our pet queries can be represented as our BA. So this is our anchor node. Apply multiple relations, how many we want, and then starting from our fixed node, we reach a set of possible answers, okay? And we're gonna be calling this our computation graph, okay? In the case of a pet query, our computation graph is a chain, okay? So one node at the beginning, our anchor node, each pet query, each relation will be one edge in our chain, and then we reach the set of answers at the end. So let's go through an example. How does this work? So we have our query, which is, where did Turing Award winners graduate? Our anchor node is Turing Award, BA, and then we have two relations, right? We have win, and then we have graduate. So given our knowledge graph, how do we answer this query, okay? And we're gonna just be doing a traversal here, all right? So again, Turing Award, our anchor node. Next step is we traverse all the win edges. We get Pearl, Hinton, Banjo, and this is our intermediate set of possible answers, and then we expand on those, okay? So we traverse all the graduate edges from those candidate nodes, and then we find this set of universities, okay? And this is our answer. Now, what happens if our knowledge graph is incomplete? Give it a shot before I give you the answer. So try to think about why that would be a problem. Pretty much every answer that you come up with might be a good one, so don't be shy. What could possibly go wrong here among the many things? You will not have all the possible intermediate nodes. Yes, that's one way of seeing that. The other way is, imagine if we do completion. All in a sudden, we don't have any more fixed edges. We actually have probabilities assigned to a lot of edges, right? So say our link prediction algorithm, the output is a softmax, and then it will give us a ton of probabilities on all these edges. Now, all in a sudden, this graph has become incredibly dense, and then if we do the traversal, we're going to be traversing basically a good chunk of the graph at every step, okay? So these are the two trade-offs. Either we miss a lot of information, or we have an exponential explosion of how much we have to traverse, okay? So can we basically do this link prediction first and then try to answer the query? And the answer here is no, because our knowledge graph is going to be extremely dense, and the time complexity for the traversal is basically in the order of b to the power of n, okay? Like at each step, we might be traversing pretty much all the nodes in the knowledge graph, okay? So definitely an intractable problem if modeled in this way. So how are we going to solve this? And as usual, embeddings are coming to the rescue, so that's why we started to talk about them long ago. And what we do here is we're going to have exactly the same path query as before, but what we hope to achieve is that instead of working straight on the graph, doing traversal, we're going to be working with all the embedding vectors of our entities and relations, and at each translation step, we hope to get close to the actual result of our query, okay? And at the end, basically, once we traverse all our paths in the embedding space, we reach Q. How do we get the answer? Again, we go and find all the possible neighbors or the close neighbors to Q, and the complexity of that step, now it's linear in the size of the graph. So we're not working anymore with something to b to the power of n, but it's going to be in the order of the number of nodes in the graph. I think there was a question coming. Yeah?
Sample in the last case, like when we have a probability distribution over the basically softmax is giving us a probability distribution over all the possible. We can sample any k number of nodes based on that distribution.
You mean in this case? Yeah, of course. So this is an extreme picture of how bad things can go. Of course, you can sample, but then basically you're starting to bring in part of the benefit of working through the embeddings, okay? So at this point, it's much better to do it straight in this way, okay? Because at each step, rather than sampling, you just have to move in the embedding space and then find the neighbors only there, okay? So at any also, sampling is clearly a workaround and will lower your recall because you might be dropping nodes that are actually useful, okay? Question?
For doing this like many steps in the embedding space, and you were training such that you were epsilon close for each relation, won't those epsilons potentially add up?
Of course,
so that like a real relation could be like outside of your new neighborhood?
Great question. So I will rephrase it as the longer is your path query, the more error you are introducing in the answer. And of course, yes. But again, we moved from deterministic, possibly correct answers to an approximate approach, as you always do when you work with embeddings. But we will see that results can be extremely good, like in the order of 95% F1 or even more. So, you know, we're happy enough with that because it's a retrieval task, so we don't have to be correct.
For this, do we also, the negative sampling, do we also corrupt only the head or tail entities, or is the training work different?
So the question is, if understood correctly, during training for this task, do we do the same corruption of the triplets as we do for TransZ? The answer is, we don't train for this task. We train for the TransZ task, for example. Let's keep in mind TransZ, okay? We just generate our embeddings for the entities and the relations, and that's it. Now we are just executing the queries in our embedding space. So the the training process is not in any way optimized for the task of answering path queries or any other kind of query. Okay? Great.
So there are two types of relations. One is for trans E and one is for trans R.
No, sorry, I probably made confusion at the beginning by introducing both models. You can model your knowledge graph with TransE, with TransR, with anything else that we might be seeing later, and you use one at a time. Okay, so once you learn the embeddings of your nodes, of your entities and relations with a certain model, these are the embeddings that you're going to use. The reason why I showed you multiple models is because each one of them comes with an advantage. So each one of them comes with the ability of modeling certain relation types. So if you know that the vast majority of your relations, have to support compositionality, then you will be modeling your knowledge graph with TransE and answering the queries through those embeddings. Okay? Great. Question?
Yeah. I'm not sure if you're going to answer this earlier, but you said that on the previous slide, you were talking about, creating like a dense graph and completing the graph itself and it'd be probabilistic. How do you decide on those probabilities? Is it based on, how do you decide on the probabilities of each link that you are filling in?
Okay, how do you set the probabilities of the edges we are generating in the knowledge graph? It's very similar to the answer to the question I was answering before with her. It depends on the radius of your nearest neighbor search. So if you decide that within a certain Borel radius X, those are good candidates, you will assign high probabilities there, and then you can have an exponential decay based on the distance of all the other nodes. That's one way of doing that, but there are a lot of other link prediction techniques. So this applies in general. The idea is you do link prediction first. If the output is probabilistic and is not Boolean, you can incur into this problem when you do the traversal.
Because I assume there might be other methods that take into account your confidence in the relation representation in the first place, maybe? Like depending on how many examples you have of that
course.
link.
Yeah, exactly.
Or how many correct ones you end up finding when you do prediction.
Of course, yeah, great point. If you have a relation that appears much more often than others, then you will trust those results. Rare relations, probably not even worth to bring them in the training process. That's why the training datasets that I talked about at the beginning are all relatively small, and they try to work with relations that appear often enough so that the model can learn something.
So both the models that you discussed, TransE and TransR, so both of them wouldn't fail on this kind of a path query, because with TransE this query can result in a n-ary relationship between the entities, and in case of TransR you cannot combine all the relations.
Correct.
Relatively.
Correct. Yeah. So what you can answer with TransE is very limited, but with TransE you can think that you can take one candidate at a time, expand that candidate, do the same. Okay, so it makes it slightly slower, but at least you can still support path queries in that case. With TransR, for the reason we were discussing before, then it's out of the question. Yeah, correct. Anyone else?
Okay, could you go to the next slide? But it looks like this graph is just a compositional of relationship. So VA plus R1 is actually an empty, and this empty plus R2 is a new empty. So this seems to be requires the relationship to support compositional properties.
I'm not sure I understood the question. I'm sorry. So what is empty exactly? So we start
VA
from
plus R1, is it an empty?
empty,
Empty.
an entity.
Yeah.
Yes. So it doesn't map necessarily to an entity. We're working on an embedding space here, right? So you can take, for instance, the closest entity to that query vector. So you go from VA, our starting entity, you apply the R1 relation, it will go in a certain area in your embedding space, and then you will have close entities to that vector. Okay, and you can pick the closest 3 ones. Okay, like we are in this example. You start from Turing Award, you apply the win relationship, and then it will bring you in this area where you find Pearl, Hinton, and Banjo as neighbors of that vector, okay? And you choose each one of them to further expand your query. Make sense? Okay, great. Let's move forward then. Okay, so let's go into detail now exactly how this query is executed, so that hopefully it will make it also clear up your doubts. So again, it's where did Turing Award winners graduate, and on the left, we're gonna have our computation graph, and on the right, you can see what happens in the embedding space at each step, okay? So we start from Turing Award, it's here in our embedding space, we do the projection of our relation, which is win, and then this vector will bring us in this area of the embedding space. We find these three very close neighbors, and we decide to expand on each one of them, okay? And this will bring us now to our answer. So the R2 will bring us to this point Q in the embedding space, and we'll find these universities projected close to that, and that's our set of answers, okay? So that's the easy way on how to answer path queries through our embeddings of the knowledge graph. Now, let's move to a more complicated class of queries, which are conjunctive queries, okay? And let's go, the example now is the following, is not only people who won the Turing Award, we want to know where did Canadian citizens with Turing Award graduate, okay? So not only we're gonna have people that are Canadian citizens, but we also want them to have won the Turing Award, and as you can imagine, there will be an intersection here at a certain step, okay? And similarly to what we've seen in the path queries, we're gonna find out how to do that in the knowledge graph just by traversing. We're gonna find out that it's not a tractable problem, and then once again, we're gonna solve it through embeddings, okay? So how do we do this? By just traversing. We have two anchor nodes now, right? We have Canada, because we want Canadian citizens, and we have the Turing Award, because we want people who actually won the Turing Award. So we start from our first anchor, Turing Award, we traverse by the relation win, and then we reach Pearl, Hinton, and Banjo, okay? So this is our partial answer for the Turing Award. Then we do the same from Canada, and we traverse by the citizen relation, and we get Hinton, Banjo, Bieber, Prime Minister of Canada, and so forth, okay? Now here we need to take the intersection, right? We clearly don't want Bieber to be a Turing Award winner, so we get Hinton and Banjo, and this is our intersection. And then for each one of the viable intermediate results, we are gonna find the universities where they graduated, and this is our answer, okay? So once again, in the ideal world, if our knowledge graph was complete, this will be extremely easy, right? We're just doing a small graph traversal, will be super fast. Again, the problem is the completion, what we talked about before, the fact that there are probabilities assigned to these edges, or there are a lot of facts missing. How do we bring this problem now to the embedding space, okay? Same intuition as before, left computation graph, right the embedding space. We start from our two anchor nodes, we apply the win relation, we apply the citizen relations, we get Q1 and Q2, and each one of them will return a set of candidates. Now we need to find the intersection. Why do you think this is a problem? Or can you think of what is the intersection of two vectors in an embedding space? I'm going to answer it now, because if you didn't hear about deep sets or anything like that, it's not exactly intuitive. But you can see why there is a problem, right? We're basically stuck here. We just know that there are some candidates from Q1, some candidates of Q2. How do we do this in the embedding space, okay? So we need a neural intersection operator. So we need something that allows us to define what it means to find the intersection between two vectors. And how do we want this architecture to look like, okay? So our input is all the query embeddings. We saw two, there could be n of them. We don't care, how many relations we have at the beginning. Our output is the intersection of this query embedding, and there is one very important property that this architecture has to have. It needs to be permutation invariant. So what it means, if you think about it, the intersection of A with B or B with A has to be exactly the same. And for those of you who have studied neural nets, you know that it's hard, or in general, a standard neural net is not permutation invariant. The reason is you're doing a lot of matrix multiplication throughout, to do the weight propagation, backprop, and so forth. So per se, a neural operator is not permutation invariant. So how do they solve this problem, okay? So the architecture looks the following. Again, it's a very high-level description. I just want to give you the intuition of what's going on. So we have the different vector embeddings for our input queries. We go through a first shell of neural network that we call phi, and this neural net will give us just a set of features for each input vector, okay? So we extract basically how important is a certain query, and we extract a feature vector for each one of them. Then we apply a permutation invariant operation, which could be the mean, could be the sum, whatever you know from math that is permutation invariant. Apply another layer of neural net, and then we obtain the vector embedding of the intersection query. Now, what you need to care about is the fact that our phi and beta will end up in our training, so there will be parameters that we learn, and then we learn how to do this intersection correctly. And the architecture is called deep sets. There are papers about it, so if you're interested, if you want to know more, you know what to go and check. But this is a problem that is solved in some sense, okay? So we're going to use it now to work on our intersection. So now that we found, sorry, question?
What is the purpose of the first neural net? Because in some way, Q1 to QM are also learned from some data, right? There are some embeddings in the latent space.
Yeah.
So can we just remove phi and then take this permutation invariant operation and then apply a neural net to?
Okay, so the question is, can we drop phi and leave only the rest? Yeah, so the advantage of phi is the fact that it's actually extracting features of the combination of those query vectors together. So those query vectors are trained in isolation in some sense. Let's say they come from your TransZ, okay? But when you pair them up together, basically what phi does for you, it tells you this query is more important, or this query should be considered more and this query should be considered less. So it's kind of a weighting scheme, okay? To make it in a very simplistic terms, okay? So it gives you this weighting scheme, then you go through the mean, and then you get another embedding, okay? Thanks for the question. We bring in the permutation invariance there.
Phi is not permutation invariant. If I get a different permutation.
Yeah, up to there, we're still not permutation invariant. So we enforce it here, and this one is a simple MLP, and the rest, they prove that it's still. Sorry?
The whole architecture is not permutation invariant.
Not each single step, but then they guarantee that your output is going to be. Make sense? So the first step is not.
So even if I mean them, the output will be different.
So phi produces a different output given the ordering, but then after we apply the mean, so no matter how you shuffle that ordering, the features will be the same, right? Because this neural net works element-wise. So it produces a set of features per vector. And then here we make it permutation invariant, and then make sure that this is not even a neural net, it's a simple MLP, and the rest stays permutation invariant. Okay? Great. Anything else? Let's go then. We're kind of running out of time. Okay, so we have our computation graph now. We found out how to solve the intersection, and now we finally have an understanding of what it means to get the intersection of Q1 and Q2. Now we know how to project this. Once again, we end up in an area of our embedding space, take the neighbors, and that's our answer, okay? So now we solved conjunctive queries in our embedding space. How do we do the training? Everything else pretty much looks as TransZ, so it's still in the order of d dimensions per node, d dimensions per relation embedding, and then we have our new phi and beta, which are coming from this deep sets architecture, but likely the number of parameters there does not depend on the graph size, okay? So basically all of this to say it's the same training strategy as any of the TransX embedding classes, and it will have the same complexity as all of them, okay? So that's why before I answer for the path queries, we don't even have to change at all the training, and to serve the conjunctive queries instead, we actually need to learn these deep sets architecture to make sure that we can do the intersection, to answer your question from before, okay? Okay, so now the whole process, just to go through it once again, we get a query, an answer, and then we have our negative sample v prime. So what we do is we embed our query queue, we calculate the distance between valid answers and corrupted ones, we optimize the loss. So all of this is basically like TransZ. The way in which we do query evaluation, we're given a test query queue, we embed it. For every node in our knowledge graph, we compute the distance, okay, between our V and the query, and then we sort by distance and rank all the nodes to find the answer. So we decide we want to return 10 answers in total, we sort them by distance, take the top 10 out of that sorted list, and that's our answer. Question?
Like something that we manually get for this particular query, because it's not like we can traverse the tree to get to it.
So your question is this answer set something that we manually get? We are not traversing anymore, right? We moved away from the model where we traverse the knowledge graph. We're just moving in our embedding space. So if by manually you mean wherever our queue projects us, then we find a ball of radius R, and then we take all the entities within that ball as the candidates, then yes, that's exactly what we do. So in that sense, it's manual, because we're not traversing, but we're using the distance between the embeddings to find the answers. Make sense? Question?
If you're visualizing embedding after the deep set, does it actually fall in between the two embedding for the other, for the intersected?
You mean if you visualize IQ1, Q2, will it fall in between? Yes, if you do like a TSNE projection of this embedding space, you would expect that to be in the neighborhood of Q1, Q2. The problem is, given that usually you go from hundreds of dimensions to 2 in TSNE because you want to visualize it, there are some artifacts that creep in your actual visualization, so sometimes you will not see it close. That's why there is a lot of work in visualizing high-dimensional data to avoid those problems. But most of the times, yes. I'm going to show a TSNE if we make it on time and the end based on one of these techniques, okay? Question?
In your training process, where do you train the deep set architecture?
We're not going to see it because it makes things even more complicated. But the idea is it's very similar to the TransZ architecture, but if you change the parameters phi and beta of our deep sets, if it's not correct, then it will do bad on these conjunctive queries. So if you train and you have some ground truth on these conjunctive queries, so you know what the answer should be, then you train phi and beta in such a way that they produce the right answer to these queries, okay?
And also many a neural network.
Correct. Yes. So this is a joint training. We're training both the embeddings and that very small neural net. Okay. Yeah. So that's why I said before for the path queries we could just do TransZ, and here we have to add this layer of complexity represented by the intersection operator.
So in here we are training both the tasks together. Like first, like generating the embeddings for the knowledge graph, and then doing the query embedding?
Yes, are we training this together? The answer is you could do them separately, clearly. So you can first generate embeddings, and then given the queries and their answers, you try to find the best parameters for phi and beta. In general, whenever you can do joint training in life, it helps you because you have more mutual information. So if you come up with an architecture that allows you to train everything in one shot, you will do that, yeah. Great question. Anything else? Let's move then. Okay, so what are the limitations of this model? We've seen it before. Taking intersection between two vectors does not follow any intuition, so we kind of found an elegant hack to overcome that problem. And at the same time also, how can we better model these sets? So what you were asking me before, are we choosing arbitrarily our ball of radius R? Can we find a framework that model these sets in a smarter way? And the way to do it is basically to find a more expressive geometry to embed these queries. Rather than just working with vectors, we're going to be working with boxes, okay? So we're going to have hyperboxes in our space that will enclose the set of entities that answer our query. So that's the last part of the lecture. We're going to be talking about query to box, which is a way to reason on knowledge graphs through box embeddings. What are box embeddings, first of all? Okay, so rather than having our vector, we embed queries with these hyperrectangles, which from now on we're going to call boxes. So it's easier for me to pronounce. So a box is represented by a center and an offset. Okay, so means that you will have one coordinate per dimension. Okay, so we will tell you what is the center of this box, and then you will have one offset per dimension. Okay, so it's an hyperbox. On each dimension, you will know how wide is that box there. So if you are in 2D, like we're here, a center is 2 coordinates for your center point, and then the offsets are the 2 sides of the rectangle, okay? And you can generalize these to multiple dimensions. So this is going to be the key difference from now on, okay? Now, we said that taking the intersection of 2 vectors does not follow any intuition. That's why we have to pass through deep sets. But the intersection of boxes is very well defined, right? You can visualize that in 2D and 3D in your brain very easily, and it clearly generalizes also to multiple dimensions. And similarly, we said we want to find a more powerful abstraction, rather than just having this nearest neighbor search to get the answers. Instead, we want to use boxes which are more powerful, and we're going to be able basically to project the center, control the offset of the boxes. So like every time we want to find intersections, we can decide to shrink the boxes, make them wider, and so forth. Okay, so now we have basically more parameters to model in query to box. What are these parameters? Okay, so for the entity embeddings, we're pretty much doing the same as before. Okay, so each entity will have d dimensions, and the reason is entities can be seen as 0 volume boxes. So you only have the center. So you have a point in the space that represents an entity, and you don't need a box around it because we have the exact coordinates of that entity. Now instead, relations are actual boxes. Okay, so that's why we have more dimensions. So for each relation, we have a set of dimensions for the center and a set of dimensions for the offset, as we explained before. So that's how you define an upper rectangle. And then we're going to have, once again, our intersection operators, which look exactly like the deep sets architecture we've seen before, but now we're going to apply it straight to the boxes. Okay, so we're going to use deep sets to realize, given multiple boxes representing relations, how do we take the overlap between them? Okay. Same example as before. Let's walk through the computation graph and embedding space, and let's see what happens now that we have boxes. Okay. The query is the same. Where did Canadian citizens win with Turing Award graduate? So we have 2 anchor nodes. We start at the beginning. First thing, if you recall, we were doing is how do we do the projection? So things here change already, right? We said now relations are not anymore vectors. They're actually projecting boxes. So let's define now what is a box, okay? So as we said before, we're going to have this projection operator, which goes from specific starting box and a relation to a new box. And what happens here is it's going to be a very easy operation. We just sum the centers, okay? So this is going to be a translation operator for the center that moves from here to there. And then we're just going to be summing up the offsets. So our box will get larger. And if you recall one of the questions from before, this captures the intuition that at each step in your path query, you are introducing error, right? So that's exactly why our box is becoming larger. At each step, we're going to try to capture more information. We're going to basically try to enclose more entities in our box. Okay? So that's why the size grows. So that's our projection operator. Okay? So first step, now we know what to do. Basically from Turing Award, rather than drawing a vector and then saying we're going to be taking those neighbors, we find the box which encloses the entities that we care about. Same from Canada citizenship, but now we need the intersection, right? And visually, you can already see it. So it's going to be this area, but how do we actually compute it, okay? So we had this projection operator before. Now we're going to have an intersection operator that goes from a set of boxes to a new box that represents the intersection. And here the difference is the center is a weighted average among all the centers in the set of boxes, and we want our new offset, rather than becoming larger, we want it to shrink, right? Because we're finding the intersection between them. So how do we do that? Again, I put the paper at the end. I will try to give you the intuitions. There is a bit more happening under the hood, but ideally what we do is we are going to have a dimension-wise product between the centers, and we're going to learn a set of weights. Okay, so these weights are going to be learned, and they will tell us which component of the center should be taken into account when we do the translation, and which components count less. And at the same time, we said we want to guarantee the shrinking of our boxes, right? We want to make them smaller. So what we do here is we're going to take basically the smallest component per offset among all the boxes, and then apply it to our new box. And that's where we have, again, the deep set architecture, because as I was saying before, deep sets allow us to find which box counts more in the queries that we want to produce. Okay, we said before that the deep set will give us feature for each query. Okay, so for those component of the queries that count more, this will give us a higher score. As you recall, the sigmoid squashes between 0 and 1, so it will leave us basically the intersection only of the boxes that are more important. Okay, so this just gives you the intuition why it's going to be shrinking. So now we know how to do this. We get the intersection, but we have one step left, correct? Because now we want to find out where did they graduate, right? So same thing. Now, instead of projecting from a box of 0 size, so of 0 offset, we're going to be projecting from a box that actually has an offset. But this is completely natural now, right? We're not starting anymore from an arbitrary point, which a deep set gave us as an output. We're just starting from a smaller box, project from there, and get our set of answers from the new resulting box. Okay. So all in a sudden, we went from a framework that had some steps that were not intuitive to something where everything is very well defined, and we can just work with boxes through the end of our solution. Any questions? Or we go quickly through the training? Okay, let me give you a super quick overview of how the training looks like. So we have this, we want to define now what is the entity to box distance. So if you recall in TransZ, we were defining what is the distance between head, relation, and tail, and we want to minimize basically the distance. Now we're working with boxes, so we need the concept of a potential answer to a query when it lies outside of the box and when it lies inside. So we're taking basically an L1 distance, and the way in which we get it is when something is outside, we take the full distance, but when it's inside, we're going to have a weighting factor alpha, which is between 0 and 1, which sort of discounts the distance if you are inside the box. Okay? So the way in which you should read is you penalize an answer if it lies outside the box quite a lot, but if it's inside, the distance counts very little. Okay? So alpha is a parameter that usually is manually selected, but everything else is going to be learned. Okay? So once we have this distance, now we can apply something very similar to the TransZ training that we've seen before. So given a set of queries and answer, now we're going to have our B are the valid answers, B prime are the wrong answers. So you can think of them again as valid triples and corrupted triples. And there will be the upper part of our loss function. Basically, it tries to minimize the loss, so minimize the distance of the valid triples, okay, so our B. And the bottom part will try to minimize the loss once again by maximizing the distance within the query and triples that are not valid and answers that are not valid. If you are asking yourself, why is it a log times sigmoid and so forth, just get this intuition. These functions look like that, okay? So if you are within the margin, then the loss is very low. And once again, if you are outside of the margin here, the loss is very low. And we penalize when something is outside of the box there, and we penalize if something is getting outside of the box in here, so it's larger than our gamma margin, okay? So looks very similar to TransZ. It just replaces the distance between vectors with distance between boxes, okay? So that's the only thing that you have to keep in mind to understand where this is going. Question?
How can we prevent this learning from just make all the boxes arbitrarily large such that the losses are small?
Okay, great question. How do we prevent that we make the boxes very large? And the way you prevent that is by having a set of validation queries where you need to return correct results. And if your boxes are very large, you let them grow arbitrarily, you will always return each possible entity in your knowledge graph, right? So what you will get there is, say you measure your performance with precision and recall, your recall will skyrocket to 100%, your precision will be abysmal. So that's one of the objectives that will allow you not to just grow arbitrarily the size of your boxes, okay? Great question, thanks. Yeah.
Empirically, do you know if there's anything about which relations tend to have larger volume boxes and which relations tend to have smaller volume boxes?
Oh, that's a great question. I don't think, I cannot think of a good answer. I don't know even if the author thought about that. It's kind of hard to think about the size because basically you would have to compute the volume in the dimensions, and that I think it depends a lot on the knowledge graph where you're training it. Okay, so it might be the case that the same property between Wikidata and Freebase would have a completely different size of the box just because of the number of occurrences it has in the data set. So I think it's hard to come up with an intuition of how big they will be. It's much more data-driven, I would believe. Yeah, good. I will tell the authors to think about it. It's a great question. Anything else? Okay. So if I had time, I would try to show you also very quickly that Query2Box supports altogether symmetry, composition, and one-to-many properties. I will not have it, so paper is here. If you're curious, you can go and check it. I will skip these slides. Possibly like, yeah, well, I'm not going to be able to make it. Another thing that I will just give you the teaser so that you know it also supports this. There are also, as we said at the beginning, other type of queries apart from the path queries and conjunctive queries that we've seen today. So for instance, something similar to what we've seen before, but with a key difference is where did Canadians with Turing Award or Nobel Prize graduate, okay? So it's not only conjunctive, but there is a disjunction there. And this conjunctive query plus one disjunction queries are called existential positive first order, comes from first order logic. Just keep in mind that if you go through Query2Box, they also support this kind of query, and this is a very novel result from like a few months ago, okay? So that's pretty much today's status on what kind of query you can answer efficiently on massive knowledge graphs, okay? So if someone asks you, can this very complex query be answered? You go back to the slides and you will have a clue if it's possible to do it in a fast way or not. Okay, let's go super quickly to the experiment. I just want to convince you, how well this is working. So as I told you from the beginning, we're seeing the FB15K datasets. I've added a few columns here. So remember, it's roughly 15,000 entities. The number of relation varies. But here we have this split where we keep most of the training edges, and then we leave out validation edges and test edges. So all these experiments are not running on the full Freebase dataset. Rather, they're running on a slightly incomplete version of this FB15K, and then they try to predict those queries that will use the validation or test edges, okay? So basically, they try to see, can this model find that there are certain valid answers with the edges that we dropped arbitrarily, okay? So these are usual training and test split, and the way in which they made the task also much harder is that they train on very simple path queries and conjunctive queries, okay? So 1 path, 2 path, 3 path, and very simple conjunctive of 2 and 3 size. And then they test on unseen conjunctive queries, which are like a composition of path or this weirder structure, or also on union queries. So this makes the task even harder because all the queries that they try to see if the model generalizes to or not are completely different from the queries that they train on, okay? Now, one question that you might be asking is, how do we generate these queries? Because you're not going to have people writing the queries manually to you, right? And you want a ton of them so that you have a lot of data to train from. So they have a couple of strategies to do that. Basically, they pick randomly a root node, and then they do traversal in a smart way so that they can generate these examples of conjunctive queries that I was showing you there below. Of course, they put effort in removing the generated queries. So for instance, if they're traversing a symmetric relationship, then they drop it, because here this is not a path query in the end, it's just a loop that goes back to the same entity, and so forth, okay? So they have a way basically to generate, and then the way in which they run the queries, they do it in reversal. So they use v1, v2 as anchor nodes, traverse, and find out if the answer is actually the root that they started from. Okay, so these are the stats. So again, to give you an idea, that's why they need to generate, because they have hundreds of thousands of training queries and tens of thousands of validation and test queries. And in the last few minutes, as I said at the beginning, let's try to go through a visualization to get a clue of how this is working exactly, okay? So we're going to use a slightly different query here, which is on Freebase. We try to list all the male instrumentalists who play string instruments, okay? And so what we do is we take our embedding space, we map it with TSNE to a two-dimensional space, and we try to visualize the query result step by step, okay? So first step, we embed our 15K entities in TSNE. Looks possibly less clustered than one would hope, and that's kind of intuitive. Why? I mean, we're not clustering communities of completely disconnected entities. This is an almost complete graph, right? So they have a lot of edges connecting. There is a lot of mutual information between these entities. So this is our computation graph of the query, okay? Relatively similar to what we've seen before, path plus conjunctive at the end. How is this going to work? First step, we start from our string instruments. Our blue, small blue node there is our anchor node, okay? So we start from there. And now we take all the string instruments, okay? So we do the projection. So we say we have the string instrument node. We take all the instruments that belong to that class, and this is our group of string instruments there. So we get a violin, viola, cello, and so forth. And the performance of this initial query, we get 100% true positive rate, okay? So this query is executed perfectly by query to box. Next step, you see, follow the underline. So now we have instrumentalists who play string instruments. So we do two projections, each one of them with boxes, as we've seen before, and we have a slight drop in terms of true positive rates, but we're still at 98%, okay? Now we've done the first part of the path query, and now we have to do the second one. So we have to find all the male people in our data set. So again, start from this anchor node down here. We do the first projection, and we get in total roughly 3,500 men, and we're gonna be applying our intersection, and that's the final, and that's the final result that we get, okay? So we are 99.4% performance. So, you know, with this example, which is quite complicated as path queries, is an intersection at the end, we still achieve a very high true positive rate and roughly 400 answers, okay? So I officially run out of time. If you have any questions, I'm happy to take them here or offline as well. Thank you.